Okay, we are at section 25.3, combinations of capacitors. We're actually going to start putting circuits together, very simple circuits, but they are indeed circuits. So let's share um, the screen. And first, we're going to talk about some symbols that we're going to see in the circuit diagrams. The first one is a capacitor symbol. You have the two parallel lines, but notice that they're the same dimension. They're both the same length. Um, Now, some capacitors they show a flat line and a curved line. In here, we'll mainly see uh, two parallel lines. If you do see a one curved line and one uh, flat line, it's a capacitor. Then we have a battery. The battery is a uh, two parallel lines, but one is long and one is short. The long one is the positive terminal of the battery, and the short one is the negative terminal of the battery. And then finally, we have a switch. The top there shows the switch open, and the bottom shows the switch closed. We saw these diagrams in the little simulation that I showed you earlier. So these are some of the fundamental uh, symbols that we're going to use at this time. Now, parallel combination of uh, capacitors. This is a picture on the left side, figure A, a pictorial representation of two capacitors connected in parallel to a battery. And then here's the equivalent circuit diagram on the right-hand side, figure B, a circuit diagram showing the two capacitors connected in parallel to a battery. You can see the capacitor 1's on top, capacitor 2's on the bottom. The charge on one is Q1, and the charge is on the others is Q2. Um, Now, if you could take, hopefully you can see the little cursor. If you were to take a meter and put the positive probe of your voltmeter anywhere along here, or let's just start here at the battery, and put the negative terminal of your meter, the negative probe on this side. As you move the meter, you'll see that uh, this is all really connected. So you would get the same voltage no matter where you move your meter on this side. And the same thing if you move the negative on this side. This is all really one point. I mean, there's wires and stuff, but we can play with it in the lab, and you'll see that there's that you'll measure the same voltage. So delta V1 across capacitor 1 equals delta V2 across capacitor 2 equals delta V, the voltage across the battery. So the Q total is equal to Q1 plus Q2. So that's capacitor 1 times delta V1 plus capacitor 2 times delta V2. Um, so I think that's the same wording. So Q total is equal to C equivalent times delta V. So the C equivalent is equal to C equivalent delta V is equal to C1 delta V1 plus C2 delta V2. So we can using the distributive property, since delta V1 equals delta V2, that equals C1 plus C2 times delta V. So the C1 plus C2 is the C equivalent delta V. So C equivalent is equal to C1 plus C2. What does all of that say? When you have a parallel combination of capacitors, you simply add the values of the capacitors. When you have capacitors in parallel, to get the equivalent capacitance, you add the capacitance of each value. Okay, now, so if you have multiple capacitors and they're all in parallel, then you just simply add them all. C1 plus C2 plus C3 plus so on equals the C equivalent. Okay, series combination. Now, here's a pictorial representation of two capacitors connected in series to a battery. And here's a circuit diagram showing the two capacitors connected in series to a battery. Now, here the Q in other words, as you get this circuit flow, the amount of charge that goes through C1 is the same amount of charge that goes through C2. So the charge is the same on each capacitor. So Q1, the charge on capacitor 1, equals Q2, equals the total charge Q. So the V total is going to distribute among the capacitors. So the V total is equal to delta V1, the voltage on capacitor 1, plus delta V2, the capacitor on C2. So that's equal to Q1 over C2 plus Q2 over C2. And if we continue, the V total equals Q over C equivalent. So Q over C equivalent is equal to Q1 over C1 plus Q2 over C2. So we'll see that the C equivalent, let's be careful here, because this trips up a lot of students. 1 over C equivalent is equal to C1, I'm sorry, 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Now, that's not the end answer. And a lot of students will put this at the end answer. You have to take the reciprocal of the sum of the, you have to take that sum, 1 over C1 plus 1 over C2, and take the reciprocal in order to get the C equivalent. So don't just add the reciprocals of the capacitors and think you're done. You have to take the reciprocal of the total to get the equivalent capacitor. So when you have a bunch of capacitors in series, the 1 over the C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus so on. Okay, two capacitors are identical. They can be connected in series or in parallel. If you want the smallest equivalent capacitance for the combination, how should you connect them? In series, in parallel, either way, because both combinations have the same capacitance. Well, that's not true. But what you want to do is you want to connect them in series. In series will give you the smallest combination. And that's the end of this section, but I want to deviate. I want to explain a little something. I told you about the equation that, let's see what, come on, 12. All right. I told you about the equation. Let's stop this share and share the iPad. And it'll come up in a bit. I told you about equation 25.3. The C is equal to epsilon 0 times the area divided by the distance. This is going to be very important. So let's look at the a parallel combination. We're going to, oh, there's my pen. We said that C1 or C equivalent is equal to C1 plus C2. And for the purposes of discussion, let's leave the dimensions, the area, these are equivalent capacitors, so that the area is the same and the distance is the same. So that's equal to epsilon 0, area 1 over distance 1 plus epsilon 0 times area 2 over distance 2. Now I said that the areas and the distances are the same, so let's not make that distinction. Now, if we wanted to add these, it's simply 2 epsilon 0A over D. And so basically what we've done is we've doubled, you have an area here and you have an area here, an area here, and an area here. this distance right here is the same as this distance here, and we haven't changed the distance, but we are increasing the area. Oops, excuse me. So this becomes double the area. This becomes double the area. The distance between them is the same, but we've doubled the area. Now, let's look down here. 1 over C equivalent is equal to 1 over C1 plus 1 over C2, and that's equal to 1 over epsilon 0A over D. Remember, they're the same shape, and that's 1 over epsilon 0A over D. So if we invert each of those, we end up with D over epsilon 0A plus D over epsilon 0A. And you see that it becomes 2D over epsilon 0A. So basically we have the area, this area is the same and this area is the same, but look what we've done. We've increased the distance, whereas the distance for one of these capacitors is just D. Now we've increased the distance between the plates, so this is 2D. So by remembering this equation, C equals epsilon 0 over times area divided by the distance, you can remember the formula. In parallel, it's a straight addition, and in series, it's 1 over the C equivalent is equal to 1 over C1 plus 1 over C2. But remember, to get, so C equivalent for a series is equal to 1 over C1 plus 1 over, let me make that look more like a plus, 1 over C2. So you need to take the reciprocal of the addition before you take this. Now, let me show you a shortcut. I know we're running long on this particular video, but let's look at let's not assume that the C1 and C2 are equivalent. So let's do C equivalent is equal to 1 over C1 plus 1 over C2. Now we want to combine those. Well, let's get the common denominator. So that's 1 over C2 over C1, C2 plus C1 over C1, C2. I think everybody should understand what I'm doing here. So now C equivalent, we have a common denominator in the big denominator. So that's 1 over C2 plus C1 over C1, C2. Now let's take the reciprocal. C equivalent is equal to C1, C2 over C1 plus C2. That's a little shortcut. When you have two capacitors, you can do this. C equivalent equals C1, C2 divided by C1 plus C2, and you'll get an answer. Now, if you've got more than two capacitors in series, this doesn't work. And I don't know a little shortcut formula for doing that, but you can always do 2 at a time, and then do that for the, get that C equivalent, and then do the same thing. Then we just cascade them. Do it again for the next C3, C equivalent plus the next C3. But anyway, that's a little shortcut. I'll post these notes, these additional notes, on the same page I post the video. Okay, that's it. Sorry I was long-winded, but I wanted to give you this information.